Hello students, welcome back to the lecture part 2 of our lecture 3. In this lecture we are going to discuss the concept of movement. What is movement? What is the basic formula to calculate a movement, and what kind of problem we can have to deal with the moment. So for example, we have this wrench and a force is applied to the end of the wrench, which is actually trying to rotate the wrench about an axis z, and there is a distance d as represented here. So this force and d both are important, but there are a few more things important. Now if you look at the definition, it says the tendency of a force to rotate a body about a point or axis. So we are actually trying to measure the tendency of this force that is trying to rotate a body about the axis z. Okay, now the formula here is given as force multiplied by the d. D in this case is very critical, and we must know how to get this distance d, because it is actually perpendicular distance from point, or specifically point of rotation, to the line of action. Now line of action is actually the line of action that we talked about for the force. We did discuss this in the last lectures, and it is the distance d is actually perpendicular to the line of action, as in this case is our distance d, and it has a 90-degree angle with the line of action. Okay, so in that case, when we have this distance d that is actually from that point of rotation to the line of action, and it is perpendicular, then we can use that d and we multiply it with that force to get the value of moment. Alright, so this is the basic definition of or basic formula for calculating a moment. In other words, it is also sometimes called as a torque. The wording are different, the definition is different, but eventually they both are the same thing. Here we will call it as a moment. So what we need is, we need a force and we need a perpendicular distance from that the line of action of that force. Okay, so these two things we need to have in order to calculate the moment about a certain point or axis. Now the units are Newton meter. So Newton, the force is in Newton, the distance is in meters, so obviously it's a product, so we get the units as Newton meter. Now as for the sign, so sometimes the moment will be positive, sometimes it will be negative, but the sign convention that we will use in this course will be, when the rotation is clockwise, we will take it as positive. The rotation is counterclockwise, we will take it as negative, and it's only because the direction is opposite. And to get the direction or the the direction of moment, we can actually use this right hand rule. So we just curve our fingers around about the direction of rotation, and our thumb will actually point to the direction of the moment vector. So this is the basic way on how to calculate the moment direction, how to calculate the moment and how to figure out the direction of the moment. Okay, let's look at an example where we have force that is applied in this case, and we can see that the line of action actually passes through the point of rotation, or at least through the axis of rotation. In this case, if you think about it, there will be no rotation, because the line of action is passing through the axis of rotation and there is no perpendicular distance. We have the force F, but the perpendicular distance is equal to 0. Perpendicular distance is the distance from the point of rotation, which is actually this one, to the line of action, and the line of action is actually passing exactly through this point, and in that case your d is 0, and that's why you get the moment equal to 0. Alright, now this is just one case. Now let's see another case where, if you look at this case where a force is applied, we can split this force into x and y components. Now we know how to do that. Now the y force has a perpendicular distance, okay, from the line of action, but the fx line of action passes exactly through the point of rotation. So point of rotation is this one, and if you look at the fx, the line of action of the force x is exactly passing through this point of rotation. So this force fx will have no moment in this case, because its line of action, or the perpendicular distance from the line of action of the x-axis, is 0. But we have the perpendicular distance from the rotation axis, or from the point of rotation to the force in y-axis. We have the perpendicular distance for that, but for x it directly passes through the point of rotation, so it will have no moment in this case. Okay, so we have to see which components are actually creating the moment, and which component are actually passing through the center of rotation. And if the line of action of any force is passing through the center of rotation, it will have no moment. Clear? All right. Let's go on and look at this Varignon's theorem. It states that if there are multiple forces applied on a body, like for example in this case F1, F2 and F3 are applied at different locations, then if you want to calculate the moment about point O, like for example in this case this point, if you want to calculate the moment about point O for the multiple forces, then the Varignon theorem states that the moment of force about a point is equal to sum of moments of its components. So you have to calculate the moment because of F1, you have to calculate the moment because of F2, and then you have to calculate the moment because of F3. Once you have all these three moments, you can then go on and sum them up to get the total moment about point O. So this is just the basic Varignon's theorem. And let's look at a basic example where we are trying to determine the moment, of these three forces about point A. So we have this point A right here, and we are trying to determine the moment of F1, F2 and F3. Now first thing we need to do is we need to split them in components, because these are at specific angles, and what we need is we need a perpendicular distance from point O. Alright, in order to do that we have to split them into components. So let's see. Here you see we have split the F1 into components, we split the F2 into components, and then we split the F3 into components. We know how to do that. You can watch the previous video if you are still confused on how to split a force into components. We already have discussed that in previous lectures. Alright, so once we have these components, we need to find out which components are actually passing through our point of rotation, or the axis of rotation, or the center of rotation. Okay, so we need to find out. In this case, if you look at this, F1x, now the line of action of this force is actually like this, and it is passing exactly through point A. And if you look at the F2x, it is also having the same line of action, and it is also passing exactly through point A. So these two forces will actually have no moments, because their line of action exactly passes through point A, and the moment for them is 0, because there is no perpendicular distance between the point of rotation and the line of action of these two forces. Okay, but for the rest of the forces, which is F1y, F2y, F3x and F3y, these forces will have some sort of moment created about point A, because the line of action of F1y is actually this one, and it has some perpendicular distance from point A. The line of action of F2y is this one, and it also has some perpendicular distance from point A. Then we have the F3x, which is the line of action has this one, and if you see we have some perpendicular distance here. Okay, and then if you look at the line of action of F3y, it also have some perpendicular distance from the point A. Alright, so that is why because we can extend it backward, the F3y, and if you extend it backward, it will have some perpendicular distance, okay, which is actually equal to this one. Now once we have these perpendicular distances, and then we can go on and calculate the moments created by these forces. Okay, so for example, if you look at this one, the F2x and F1x, this one and this one, they do not produce any moment about point A, because the line of action passes through point A. Alright, so their moment will be 0, there is no perpendicular distance. For the rest of the forces, let's see. For instance, for F1y, you see it is creating some, and F2y also it is creating some movement. Now you need to keep in mind in which direction it is rotating the body. For F1y, it is rotating in the clockwise direction, so whatever movement we are gonna get, it will be positive, and the distance for the F1y is 2 meter. For F2y, the distance is actually 3 plus 2, which is 5 meter, and it is again clockwise, so it will also create a positive moment. All right, now once we have these clear, we are left with the F3x and F3y. Okay, so let's see, have a look at them. All right, so we see that the F3x has a perpendicular distance of 4 meter from the point of rotation, and F3y is actually having perpendicular distance of 3 plus 2 meter. F3x is counterclockwise and F3y is clockwise. So F3y will have positive moment, but F3x will have a negative moment because it is creating a counterclockwise moment. So there is only one negative moment, and that is created by the F3x. The other, all three will be positive moments. Okay, so I hope this is clear now. So we are going to go and let's calculate the moments. So if you look at here, for the first which is first force, which is F1y, it is the line of action is this, and the perpendicular distance is this one, which is actually given as 2 meter. So we have the force 216.5, so that is this one, and the perpendicular distance is 2 meter, which is this one. So we get the moment created by F1, and it is clockwise because it is rotating in this direction. So we also mentioned this positive clockwise sign with it. Now let's move on to the F2. Since F2x is having no moment, F2y, which is 259.8, and it has a perpendicular distance, since this is the line of action, and its perpendicular distance from point A is 2 plus 3 meter. So we have 5 meter perpendicular distance, and the resulting moment of the force 2 will be again this one, 1299, and it is also rotating the body in the clockwise direction, so we have mentioned the clockwise rotation with it. Now when it comes to the third force, which is actually combination of 2, and both of these are creating moments. Okay, for example, in the F2, so only one component was creating moment, the second was not. In case of F1, only one component was creating the moment, the second was not creating any moment. In this case, F3, we have both of them creating moment. This F3x is creating a counterclockwise moment, so it will be negative, while F3y is creating a clockwise moment, so it will be positive. So keep that in mind. Now look at the perpendicular distances. For the F3x, let's see where the line of action is. So this is the line of action of F3x. Okay, so we have the line of action, and we want to get the perpendicular distance from point A. So point A is here, and we have this perpendicular distance. Perpendicular distance is in this case equal to 4 meter, which is given right here. Okay, opposite here. So it is the same distance. So that is why if you look at here, so since it is the F3x is creating a counterclockwise, so we use the negative sign first, and then you use the F force multiplied by the perpendicular distance, which is 4 meter. So this is the first moment created by F3x. The second one is F3y. It is clockwise, so we mention the positive sign, and then the force F, which is 400, and then the perpendicular distance. In this case, if you look at the line of action, so it goes like this. So this is the line of action. Okay, and the perpendicular distance of this line of action is, which is this one, this is the perpendicular distance, is equal to 2 plus 3. Okay, and that is why we have mentioned the perpendicular distance as 5, and it gives us the total moment 800. Now you must notice that here we had negative, here we had positive, but the result is 800. That means the combination of these component will give a positive value, and it is giving a positive value, so that's why the result will be actually clockwise. Okay, so also you can see here we have mentioned it as that we are taking the clockwise as positive. It's just a convention that they mentioned it. All right, so we have solved this problem, and now we know how to calculate the moments. Let's have a look at this problem where we have to find out the moment about point O. Okay, and we have a force here applied as 100 Newton. Now again, the first step would be to split it. Now let's solve this problem here. Okay, so the first step would be to actually split the force into two components. So I have this force applied, let's say at this point, and it is having 100 Newton force. Okay, and if you split it, we will get a y component. Let's call it Fy, or vertical components, and then we will also get a horizontal component, which will be Fx in this case. What we know is we have a triangle here. Okay, it's a triangle where the base is 4, the perpendicular is 3, and hypotenuse is 5. Okay, now we do not know this angle, but it will be equal to this angle. Okay, it must be equal to this angle, and this theta will be equal to this theta. Okay, all right. Now we have already discussed that in the previous lecture, where we were trying to get force into components. So if you don't understand this step, just go back and watch that. It will be much more clearer. Okay, once we have this, we can write Fx as, it will be equal to 100 Newton cos of theta. Okay, now we know that the cos theta is equal to perpendicular base by hypotenuse. Okay, and base in this case is 4 and hypotenuse is 5. Okay, so we can just write cos theta as 4 by 5. Similarly, the sin theta is equal to perpendicular by hypotenuse. Perpendicular is 3, hypotenuse is 5, so we can write it as 3 by 5. Once we have that, we can replace this cos theta with 4 by 5, so it will become 100 into 4 by 5, and our Fx will become equal to 400 by 5, so 8 by 40, that will become equal to 80 Newton. Okay, so we got the x component, which is actually this one, and now we are going to go for the y component. So Fy is equal to 100 sine of theta, and sine theta in this case is 3 by 5. 100 into 3 divided by 5, so it becomes equal to 300 divided by 5, which is actually equal to 60 Newton. Okay, so now we have found out two components, the horizontal and vertical. This one is 60, this one is I think 80. Okay, now we know these components. Do we know the perpendicular distances now? Let's see. For the 80 Newton, if we make the line of action, okay, try to change the color. If you make the line of action something like this for the horizontal component, then your perpendicular distance will come out to be somewhere here. Okay, so this is your perpendicular distance, 90-degree angle. Okay, and this distance is actually equal to 2 meters. That's given here. Okay, now that would mean that we have force 80 Newton, we have the perpendicular distance, we can find out the moment due to x component. So mx, which will be equal to 80 multiplied by 2, and it will become equal to 160 Newton meter. Similarly for the y force, if we know the perpendicular distance, let me draw the line of action for this vertical axis. So once I have the line of action, I found out that there is the perpendicular distance, this one. Okay, this is the 90-degree angle that we got. So we got the perpendicular distance and it is given as 5 meter. So we got 60 as force multiplied by the perpendicular distance and we get 300 Newton meter. Okay, again using the Verignon theorem, so the moment about point O will be, which is this one, moment about point O will be equal to the moment due to X force plus moment due to Y force. So we get 160. Also keep in mind that this force is actually rotating a clockwise, and this one is also rotating the body into clockwise moment. So in this case both are positive, so we have to take that into account, otherwise if you miss the signs your whole question will be wrong. So that comes out to be 460 Newton meter. I hope it is clear enough. If you have any questions, any issues, please do let me know and I will try to help you with that in the comment sections, and hopefully it is clear enough. So we just solved this problem, and the next lecture we are going to talk about the couple moment. It will be a very brief lecture, maybe brief video. That will be the part 3 of our lecture 3, and it is actually derived from the same principle of moment, but it is specifically made a little bit easier for when coupled forces are involved. Alright, thank you very much. This is it from me, and I'll see you in the next video. Take care. Bye.